Hello, everybody. Welcome. My name's Alex Murray, Account Manager for the North at Anatune. Thank you for joining us for our webinar on VOC analysis. Just a little bit of background on me. Before I started at Anatune last year, I think it was, I worked in a variety of technical and quality roles in a variety of environmental CROs. I guess if I had a specialty, it would be organics testing, GC, LC, mass spectrometry, and that kind of thing. Just an early caveat with this webinar. Obviously, the subject matter is hugely diverse, so we're gonna be mainly talking about environmental matrices, soil and water, but a lot of it is transferable to other things: air analysis, product testing, pharmaceuticals, all that kind of thing. So we'll get started. So why do we bother testing for VOCs or volatile organics? I guess what are we talking about? Organic chemicals with a high vapor pressure in standard conditions. I think the EU definition is anything with a boiling point of less than 250 degrees C that is organic at typical pressure. So that's a very broad definition. Thousands upon thousands of chemicals come under that. So we're generally focusing on ones that are harmful, toxic, mutagenic, have an impact on people or the environment. And they can generally enter the environment through all kinds of different polluting processes, or even just as byproducts of anything, really. I mean, they're being produced and created and generated constantly by everything: living processes, environmental processes, or manufacturing processes, anything really. So the driver for testing in environmental sector is primarily legislative. I guess corporate social responsibility is quite a new concept, so it became years ago the remit of lawmakers to force people to test. So here we've got a less of a timeline and more just a random selection of events that may be relevant. But if we start in the UK in the 19th century, the first real legislation on this kind of thing was the creation of the alkali inspectorate to control HCl emissions. I mean, that's what we're talking about really. It's environmental pollution. And the introduction of the Public Health Act around the same time, and subsequently over the next sort of 50 years, included provision of things like sanitation and water pollution and drinking water quality. And then about 50 years ago, it was sort of brought into the wider social landscape with the UN Conference on Human Environment, where we started discussing and trying to understand really our impact on the world and its impact on us. Around the same time, you saw a variety of pollution incidents. Is the Seveso disaster in Italy, which was a big dioxin pollution incident, horrific disaster. And the same kind of thing with Pacific gas and electric activated chromium incidents and all kinds of major pollution events like the use of Agent Orange in Vietnam. And people started to take a lot more of a view on this and pay more attention to what we were really doing. And then an example of specific legislation on individual compounds in 1976, the US EPA legislated on trihalomethanes. That's something we still test for today in drinking water, and they set some minimum values for that in drinking water. And then gradually since then, legislation's become more prescriptive and stringent, and an example of that is the release of the EU Water Framework Directive in 2000, which informs river basin planning and is aimed at driving an improvement in environmental water quality. So how do we do this? As with all analytical chemistry, the answer is it totally depends on the individual chemicals you're looking for, what you're trying to test it in, what the aims and what the goals of the actual testing are, whether it's continuous monitoring or batch release or construction on a site or anything really. And how you take that sample will always have a massive impact. A good example of this is an interesting development in the contaminated land sector is with the issue of BS 10176 for VOC soil sampling. And that describes a very variety of specific preservation method for VOC in soils, and how you preserve the soil totally changes how you test it, because it introduces limitations. But it's kind of an example of some desire to improve quality in this area and standardize the quality. Even water isn't as simple as just picking up a vial and scooping out some water from a river. You can even use passive samplers these days that will give you a time-weighted average that you can stick in a river or a borehole to sample over time. And if you consider air briefly, we've got all kinds of different techniques for sampling this. You can use a Tedlar bag or a vacuum canister to do direct sampling. You can use thermal desorption tubes to passively sample or adsorb and then subsequently test, or even use SIFT-MS to directly analyze the air as it is, or a photoionization detector, PID, which is a very, I guess, crude way of doing it. Regardless of how you actually take the sample, the gold standard for VOC analysis has always kind of been gas chromatography. Nothing is as selective, as accurate, and as quantitative as gas chromatography. And when you pair that with mass spectrometry, it gives you unbelievable specificity and selectivity, and the ability to scan as well, giving you an amazing toolkit to do the analysis. And the key thing about it, I guess, is that it allows you to define how uncertain the method is and how accurate the method is, which is important for analytical chemistry. There is room to mention here SIFT-MS, which is a new technique, but it's perfect for VOCs. It's literally designed for VOCs, and it can handle all of the described matrices here: air, soil, water, in a variety of different ways. But because it is quite new, it hasn't been taken up and widely adopted. So GC-GCMS still remains the most popular way of doing it. So generally, in laboratory terms, I guess 50, 60 years ago, people decided that they wanted to have an accurate and reproducible way of testing this. And purge and trap tended to be the best way to do it in the past. It involves bubbling inert gas through a sample, or sample mixed with water if it's a solid, with heating, if necessary, and then trapping those purged VOCs on either a sorbent tube filled with carbon or Tenax, or cryogenically, using a cooled nitrogen tube, perhaps. And then you desorb it in some way, using heating usually, and then transfer it onto the front of a GC column. It goes through your traditional GCMS. It's technically complex, I guess, and it's a very interesting technique. But it does have, and certainly did have, a lot of difficult drawbacks that you had to get over, particularly constant carryover risk. You could put one particular sample that was heavily impacted, and it would then ruin the entire rest of the run and the analysis. And you would have to clean and replace a load of tubing and parts in the purge and trap instrument. And that led on to a very high maintenance burden. There was a lot of maintenance and cleaning that was required, which takes time away from analysis. So, environmentally speaking, not really suited to the wide array of environmental samples that you might get. If you're dealing with very, very clean samples constantly, then it's great because it is very, very sensitive. But there was a risk. So the environmental market, CROs in particular in the UK, there's a big drive for improvements and constant innovation. Regulation is, as we've said, is constantly increasing in burden, and standard methods aren't prescribed. We don't really follow standard methods in the environmental sector. Water is a little bit different. There are some kind of widely accepted. If you're talking just a general environmental CRO, you don't have a standard way of doing it. So innovation and constant improvement is happening all the time. It's a very competitive market, very price sensitive. So there's always people that want to do things faster and better and to a higher quality. And in came kind of headspace, which is, it made sense from that point of view because it was a very simple technique. It's not at all innovative. You can do it manually easily. You can take a vial, put it in an oven, and then just take the headspace out from it through a septum, and it's easy to do. especially with an auto sampler, you can then do it very reproducibly. So the principle is simple. It's just driving the equilibrium to sort of a fixed point between the sample in the vial and the headspace above it. And then you take the sample out or take an aliquot of that air, and you inject that into your GC at a volume of 0.5 to anywhere between 0.5 or 2 mil. This is a very simplistic explanation, so do give me the benefit of the doubt. But it kind of solved a lot of problems that arose with Purge and trap. It's very quick because it's a very clean technique. All you're doing is injecting air. It's very difficult to cause any problem with carryover. And because it's a very simple technique, the maintenance. Another technique, it hasn't changed for many years. It's a really simple physical process, but the technology surrounding it has improved greatly. You've got very precise and accurate heating and agitation now that can be automated. You've got very precise syringes that can be automated, auto injectors, very high quality, precise GC inlets that control pressure very well, and very sensitive mass spectrometers. So you've got this gradual increase in quality over the years. It all came from the analytical platform, and it allows much lower reporting limits and better performance, and really to be able to do the testing very well. That said, there are obviously some problems with it. It's going to be far less sensitive than Purge and trap in general. That's because you've got an inherent dilution headspace. If you've got a 10 mil headspace of a sample in a vial, and you take 1 mil to inject, that's, you're only taking a tenth of the sample. Whereas with Purge and trap, the principle is you're trying to purge as much as you can out of the sample and trap all of it, and then transfer all of that. Associated with that, I guess, are also the GC parameters are a very difficult thing to balance with static headspace injection. When you're injecting a large volume of air and trying to transfer all of the analytes onto the columns with that, if you've got lower boiling point compounds, it's difficult to focus them, particularly if they are gaseous at room temperature and pressure. So you then use quite a high split to get good chromatography, which again drastically reduces your sensitivity because the split is effectively a dilution. The other issue, I guess, is water can co-elute with some of your boiling point compounds depending on the chromatography, and that causes reproducibility and detection. Now there are answers to these particular problems like cryocooling with the inlets or very specific column and phase selection, but that all tends to reduce the flexibility and increase the cycle time, and these are all enemies of people who want to do high throughput. I guess the biggest issue associated with headspace is that it's so reliant on external conditions like temperature, pressure, background. It's at the mercy of the sample preparation. Even the best technicians and analysts have difficulty preparing calibration standards, quality control samples in a very reproducible way. And the reproducibility requirements for environmental testing through MCerts and things are quite stringent. If you think, as an example, just spike and recovery for calibration and AQC, how do you control the solutions? If you've got VOCs that are gaseous and you take a solution out of the freezer, if you decap it, you're going to start losing. So you have to control those very stringent. And how do you preserve sample integrity when you're looking for something, when you're looking for the exact same compounds that may be present in a laboratory in huge concentrations, dichloromethane or chloroform or hexane? If you're using these as solvents in your wet lab, and you're then 2 doors down in the corridor testing for these in parts per billion or parts per trillion in samples, how do you preserve them? How do you reduce the background there? And the answer to all of these has been highly trained analysts, expensive environmental control, stringent temperature control labs, and positive pressure, and very rigorous quality assurance through stringently documented procedures. So robotics and mass spectrometry has kind of converged these days to an affordable point where you can have a sensitive, reliable analytical method that also can be automated. This is what Anatune's been doing for 15 years or more. We've seen the growth and ubiquity of headspace and Purge and trap auto samplers. You can now analyze hundreds of samples by either technique in a single run. We've got reliable and very sensitive quadrupole mass spectrometers these days that make challenging reporting limits easy to achieve, which allows smaller sample size, smaller injection volume. If we think about Purge and trap, it's come a long way since its inception. I think probably because of the continued investment in places like the US, where they did prescribe methods and they legislated methods and they said you have to do it this way. US EPA 524 and 8260 are examples of Purge and trap methods. And because of that investment, the technology's improved. You can use the Tecmar Atomics and Aquatech to automatically spike and run calibrations and quality control standards for your analysis, which gives you very good reproducibility. They've got much better and more robust rinsing and self-cleaning procedures. So it goes some way to mitigate some of those carryover concerns that we mentioned earlier. And you can also even automate methanolic extraction, so addition of methanol and agitation and extraction of the volatile, which is a great way of improving recovery in particularly challenging matrices like soils. And in terms of sensitivity, it's still unmatched. You can't beat it for very clean matrix, because you are attempting to purge everything and trap it all and then transfer all of that onto your GC. So for clean samples, and if you use, for example, an Agilent 5977 high efficiency source, you can get even lower. So for clean samples, it's perfect. But you still can't escape the fact that if you don't know what the sample matrix is like, if there's a risk that it's highly impacted, it's very difficult to escape the huge amounts of carryover and the big maintenance burden. So Anatune saw an opportunity, probably 10 years ago now, to address some of the issues with particularly static headspace, an analysis of the sweets in water and soil that we're going to talk about in a minute. But the auto sampler market was and is saturated. You can get a headspace auto sampler anywhere. Agilent have one, Tecmar have one, PerkinElmer have one. Every company you can possibly imagine does headspace in some way. So we aim to leverage automation to resolve some of the manual problems around static headspace. We designed a system to do the spiking, extraction, injection, and preparation of standards and quality controls, whilst keeping stringent control of timing. I guess we could talk about hundreds of different methods, as we've mentioned, volatiles. There's tons of different ways of doing it and things to look at. But if we think about the work that we did at Anatune, it was on this suite that you can see on the right there. It was a very typical wide range suite that has a bunch of compounds that are of interest in the environmental sector. And it's the reference there, the SCA Blue Book for VOC and raw and potable water, is a good reference for it. It details purge and trap and static headspace methods for this exact suite. And Anatune tried to address those issues I mentioned before. So everything's prepared just in time. All that's required, or was required at the time, was add in your sample to a headspace file, plus addition of whatever matrix modifiers you want, and capping. And you load it up on the sequence, and the system would do the rest. It would prepare your calibrations, prepare your QC. And the best bit about it was that there was no long wait or no imprecise wait between spiking and analysis. So you didn't need really stringent alien retentive procedures for spiking cal standards, because it would be done, and then exactly X minutes later it would be being injected into your system. Your very precise control of the whole process. And then the system uses a heated agitator and heated syringe to inject. So it's all automated. And this automation meant that it's possible to compare samples 24/7, evenings, weekends. The sample runs were no longer a slave to the working day, so you didn't have to analyze your work, and not analyze your work, but do the work based on shift systems. It gets done constantly. It gives you a lot more control over how you can actually prepare the samples. And with the latest networking technology and the ability to use the internet and TeamViewer and things, you can process the data elsewhere. You don't even have to be in the lab when the data comes off. It can be done remotely. And at the time, it was a very, very reproducible technique. Dozens and dozens of NS30 validations have been used on this system and a variety of suites, and it passed them, and it is capable of fantastic precision and bias in spike and recovery exercises. As it says there, RSDs of 1 to 3% are very common for a lot of analytes. And the older mass spectrometers, 5975C, for example, gave very low parts per billion limits of detection in water and soil, so microgram per liter and kilogram. And it gave good throughput, 15-minute cycle time in general, or even lower, if depending on the suite, which gives you, it's 96 samples in 24 hours, which when it came out was good because it's running constantly doing this. So we mentioned that need for constant improvement and innovation in all laboratories, not just the environmental lab. But it's never gone away, and certainly in the environmental sector, because we kind of did reject standard methods. We do need to be constantly improving things, and there's always demand for a better way. And besides, there were some valid concerns of our old VOC analyzer. So I've seen a couple of manual methods of calibration standard prep, where people use stocks directly from the freezer. Otherwise, the solution degrades too quickly and you won't get a linear calibration. So people ask, why would that work if the solutions are sat on top of a hot GC overnight? And the answer, I guess, that people came up with was a single-use vial of solution, or 3 uses, and then you dispose of the vial. But that's a wasteful way of doing things. The old VOC technology used elastic cords to maintain tension in the syringe. These were prone to failure at the worst possible times, usually about 5 minutes after everyone's gone home. And it needs frequent maintenance just to make sure that it's not going to do that, and you can maintain that nice run. And if you're using an older mass spectrometer and you need a low detection limit, you still have to use a lower split ratio to get more onto the column. And as we discussed before, chromatography would suffer. You get very broad peaks for the boiling point. And the systems are old. I think it's more than 10 years old, the system. So that we saw the first ones. If you've got this on a 5973 mass spectrometer, then support is becoming a costly endeavor, and it's getting harder and harder to get the parts. And with the best will in the world, the CTC rail systems, they move a lot. If you think about how much they must be moving over their lifetime, it's hundreds and hundreds of miles, because they're a very motive system. Compare that versus a GC, which has no real moving parts, just sort of solenoid valves or fans, which do get replaced easily. But the principles of the auto samplers, they move a lot. So 10 years of life is, I think, a good expectation. And I can understand why it becomes uneconomical to repair them past that. But now we have a new platform, which is the Gerstel MPS. So the new technologies that are available allow us to address some of these older issues. So if you use vial inserts, septum seal vials in conjunction with the Peltier-cooled trays that we can offer, you don't have to worry about stability of the volatile compounds in your spiking solution. Over a night or over a weekend, they're kept refrigerated. The latest technology uses more robust and less maintenance-heavy heads to move around and to do the liquid handling, so that your analysts don't have to worry about preventative maintenance constantly. It's more focused on the data and the results. And the sensitivity, even of the basic 5977B extractor, is such that low tens of parts per trillion detection limits are possible using static headspace. And if you need lower, HES, high efficiency source, imagine, will mean even lower limits of detection without having to worry about the injecting too much matrix. Headspace is such a clean technique. And of course, the system's still fully automated. You still get all of the benefits that just-in-time prep and the very reproducible calibrations and quality controls that it is capable of. It removes all of that uncertainty, and that's it. It's about removing uncertainty and driving down that uncertainty of measurement. But what else can we do? So if you're driven by throughput, how can we improve on this kind of thing? The robotics, the automated prep, and in fact in any headspace, that bit is never the rate limiting step. It's always the GC cycle that slows it down, because you're usually able to incubate sort of 12 samples or 6 samples at once. But Agilent have a new interesting option for fast GC in the Intuvo 9000, which can heat at very high rates. I think it's 250 degrees a minute, all the way up to 450 degrees. And it can cool down much more quickly than a conventional 78, 90, 88, 90 GC or a whatever you call it, air bath type GC. So that offers the ability to do GC much more quickly, potentially. Now, the consumables, I guess, are a bit more expensive for the Intuvo 1000, but when we're talking about headspace analysis or very clean air analysis, consumables are never a big burden because you don't change columns for it. They don't need it. So the technique is so easy on the equipment. So managing equipment in a laboratory is always a balancing act, and especially so when you think about automation. They always come under the sort of guise of improvement projects. Costs generally high, so it needs to be a much more efficient way of working, or higher quality, or more reliable, or lower cost per test, or one of any other number of superlatives. So it's got to be a wise investment, else the equipment does just become a paperweight in the corner, and you come in every day and you think that was money. But with technology advancing at an ever-increasing rate, I think right now there are some really interesting options to improve throughput and reduce failure rates, which effectively reduces turnaround potentially for your clients, and that's using fast GC and automation. There's a potential to improve the quality, drastically reduce uncertainty of measurement, and improve the quality of service to clients through leveraging that automation. You're removing analysts and technicians from roles that are really dull, essentially spiking of soil or water or any samples, really. I mean, it's not an interesting thing to do. Their expertise can be used to do much more complex tasks than liquid handling and standard preparation. And it's just about achieving whatever goals are your priority, really. It's whether they are strategic objectives like top or bottom line growth, or lab management objectives like maximizing the utilization of equipment and failures. Or, for me, the most important objectives, which are good science and happy, engaged scientists who enjoy what they're doing. So that's very brief. That's it from me. Thank you all for joining us and listening. Let's see if we have any questions, Martin. What are the
Hi, here I am. So there is one question. Do you want to go into that? And it's probably better if you just answer it directly, if that's right.
So we followed a brief sort of a partial NS30 guideline for our app note. I think it's app note AS141, which is available on our website. So we did the first 3 batches of NS30, but we have a variety of water industry clients who have validated this and have used it. I don't know if I'm allowed to mention their names, unfortunately, in this particular forum, but there are a large number of water industry clients who have used this platform and have carried out NS30.
There's another question in there, Alex, if you want to have a quick look about SIFT.
You mentioned SIFT-MS. Is Anatune marketing these? Can you tell us a little more? Yes, we are marketing SIFT-MS. We are the distributor for the UK for SIFT-MS, and it's if you don't know about it, it's a fairly interesting mass spectrometry technology. It uses chemical ionization to ionize volatile chemicals, not even organics. It can do inorganics to some extent as well, directly from the air, and then uses a quadrupole to separate them out. And it's very selective because you can really the fragments that are created are very specific to individual compounds. So it doesn't have any chromatography, and because of that, primarily, it's very, very fast. It can do it in real time effectively. So it's just as long as it's basically how long it takes the sample to get from the end of the sampling tube into the instrument. So it's a very interesting technology for air analysis in particular, and we've combined it with our auto sampling technology, which allows you to analyze soil and water using headspace, static headspace, dynamic headspace, all kinds of different ways. I mean, there's even ways to do it directly using our thermal absorption technology. So if you want more information, I'm happy to send that to you.
I'd also say that if you want to have a quick look on the website, there is an app note section which you can filter by technique and by instrument. So just click on SIFT-MS. And also, if you sign up for our e-apps, there'll be a button on the same page. But I'll send it around in a follow-up email after this to everybody if you're interested.
Yeah, just to actually answer Udo's second question. So the first question was, what are NS30 validation methods referred to? And he's just asked, he's never heard of them, are they UK methods? And the answer is yes. It's a specific validation protocol, or it's primarily water industry work, and it involves I think it's an 11x2 validation. So 11 batches of 2 blanks, 2 low sort of 20% spikes, 2 80% spikes based on your calibration range, and essentially you do that for each individual matrix that you're looking at. And the water sector has very specific definitions for each matrix. So it's a really rigorous way of doing it. You might end up with hundreds and hundreds of samples per validation, but the aim is to look at within and between batch variation with calibrations in between to really get an understanding of the precision and the bias of the procedure. So there is another question from Neil Owen. Hi Alex, a question and a comment. The level of automation is great and this seems a real advancement in productivity. However, people need to realize that this is just one step in the process and that the level of data production and therefore processing and validation also increases. So the question is, what would you advise on giving people the tools to review and validate the results being produced? So that is a great point. You know, at the end of the day, you being able to run more samples and generate more data, you've still got to process that. And since, I guess, when I started 10 years ago, we were using MSD Chem Station, and it was a very slow way of doing it. It was interesting at the time, but these days, software like Mass Hunter, for example, is much easier to analyze large batches, and gradually the control and the auto integration, for example, is getting more and more powerful, so that you can review automated integration very quickly, which allows you to process things in a much quicker way. And certainly, Mass Hunter is a much better way of doing it than it used to be, but it still has its flaws and very difficult to escape the fact that you will always need an analyst to think about what is being done there, because someone's always going to need to review it, even if you have all the quality controls in the world to keep control of the method. Someone needs to check to make sure they're all okay, and computerized systems may be expensive to try and get ones that do all of those checks. So Stephen Hart has asked, you mentioned soil analysis. Was that headspace and was the soil treated in any way? So there's a variety of, I guess, methods that we talked about in here. Purge and trap typically used to use sort of a methanol extraction or a water and then added to the soil and then purge. Anatune ourselves haven't done much in the way of soil testing, but our customers have done it using these static headspace techniques. And generally, the way that it's done in environmental labs, in my experience, is soil sampled and kept in headspace-free jars, and then put in headspace vials with a fixed amount of water and some matrix modifier. And what that does is it kind of brings every sample, well, the theory is that it brings every sample to a similar level of salt concentration in the water, so that you can kind of assume that your calibration applies equally to every sample. Now, because Henry's law is contributing to the partition, I don't know how true that really is, but that's the assumption we've made. But the problem with it is that it'll only really work on unpreserved soil. As soon as you start preserving soil in methanol, for example, which is a great way of preserving soil after sampling, you can't then apply that because you've got to know exactly how much methanol's been in the soil, and it's going to affect the headspace. So those methods require a different approach, potentially extraction of that methanol soil mixture and then aliquoting of the methanol and then putting that in a headspace. But either way, the automation has been proven on soil or unpreserved soil certainly, and I know people that have used static headspace with a methanolic soil extract.
But it's worth saying, if there's any questions that you think of in the wake of this, don't hesitate to get in touch. I'll be sending around a follow-up email in a couple of days, just telling you where you can watch this back if you want to, or if you wanted to share it with a colleague who may have missed the session. So feel free to respond to me or to Alex. I'll put all the contact details in there. But I guess all that remains to say is thank you everybody for joining, and thank you to Alex for leading this.
Cheers, Martin, and thank you everyone for joining. I hope it was interesting for you. And yeah, that's it.
All right. Goodbye, everybody.